So this exercise is related to electromagnetic effect. And so what is the electromagnetic effect? We know the change in magnetic flux linkage will induce EMF. And there's also a motor effect. We have discussed this. So I'll solve some questions 5 to 8 first at the MCQs. Okay, as you can see here, a proton enters a magnetic field at an angle as shown. Which of the following gives the direction of the force on a proton as it enters the magnetic field? So first thing, as this proton enter, it will have the two component. It will have the word, this will be the one component of the motion, this another component. This component will not experience any force. Why it will not experience any force? Because it is parallel to magnetic field. So this is a component which will cause a force on the proton. Because of this component, it will experience the force. Which direction it will experience the force? Because proton a positive particle. So we'll use our left hand. So our index finger or first finger represent the magnetic field, which is in this case pointing towards the right hand side. The second finger represent the direction of the motion of the particle. The particle is going in this way. So this will be a direction of the motion. And the thumb will represent the force acting on it. So index finger is representing towards right, the left hand. And your second finger is pointing upward towards the top of the page, where your thumb is pointing. Which direction the thumb is pointing? When you apply the left hand. First finger is index finger is pointing towards right, second is pointing towards the top of the page. So where your thumb is pointing, it is pointing into the screen. So that's right. So C will be the right answer. In question 6, the magnet is pushed through a coil of a wire at a steady speed, which induces EMF. You can see this we did yesterday. And the direction of induced EMF is different as it is moving in like first towards the center and then away. The magnet is then pushed through a same direction at a higher speed. So first thing, if it is pushed at a higher speed, what will happen? The time interval, it will take shorter time as what it took. And because it is moving at a higher speed, so there should be a greater induced EMF. So why C and D are wrong? Because it is longer than what is shown here. So it should be shorter, but because it is moving at a high speed, so greater induced EMF. So more induced EMF in a short time interval. That's why B will be the right answer. And why the direction of induced EMF is different? Because according to Lenz's law, EMF induced always opposes the change in a magnetic field. So if it is going towards the center, it will be opposite as it moves away from the center. So the induced EMF, the previous question, induced EMF is equals to N phi by delta T. That formula we use. And this is the rate of a change in magnetic flux linkage. Greater the change of magnetic flux linkage, greater the induced EMF. The magnetic flux density, so B is given at an angle of 55, theta is shown here. The coil has an area of 2.5. What is a magnetic flux? So magnetic flux is what? Phi is equals to B dot A cosine theta. Because like this will be the area vector. So this will also be 55. Look, if this angle is, because we need, here the angle with the surface is given 55, but we need, so this will be the area vector. Okay, this is the area. So if this angle is 55, You can take upward, it does not make difference. Our concept is that it is always perpendicular. If this is an area, I can take this as well, A. That's also fine. It does not make difference. So even if I take A here, or I take A here, it's the same concept, same idea. No difference it will make. So if this is B, the magnetic field, this angle is 55. So this angle is 55. How much is this angle? So 90 minus 55. So this is equals to 35. So now we have the cross-sectional area, and we have the B. So we can use phi is equals to B dot A cosine theta. So it will be B, the strength of a magnetic field, which is 4 into 10 to the power minus 3. A, the cross-sectional area, which is 2.5 into 10 to the power minus 3. And the angle between the magnetic field and the area, that is 35. So cosine 35 will take. What's the answer here? 4 exponent. So it matches with option B. Is it clear why we took B, not A? Because theta is the angle with the surface. We need from the area, and an area vector we always take perpendicular. So this theta is always the angle between the magnetic field and the area vector. In question 8, a beam of an antiproton, so antiproton is negatively charged, it enter a magnetic field, a uniform magnetic field. What is the direction of a magnetic field? So how we know? If we don't know, so we can, it cannot be toward, like, let's say magnetic field is into. We don't know, but we are considering. Let's say if it was into, and we will use a right hand. Why we'll use a right hand? Because it's a negative particle. So your index finger will point into the magnetic field. Your second finger represent the direction of the particle, which is towards the right hand side. So where your thumb is pointing when you apply the rule, your first finger is pointing towards the screen. Your second finger is pointing in the direction of the particle towards the right. So where your thumb is pointing downward. So if the thumb is pointing downward, it means the force is downward, and that's right. The force is downward, that causes a deflection. If the force was upward, then what will happen? It will deflect, but in opposite direction. So it gives an idea that it's, so if we don't know, we will consider whether it is in or out. Let's say we took in and our force is downward, but the particle was moving in opposite direction. So the magnetic field not be in. In that case, the magnetic field will be out.